In this video, we are going to be looking at gravity. This will be our first introduction to gravity. We'll talk about it more later when we talk about circular motion. But for now, we'll get our introduction. Specifically, we're going to talk about something called free fall, which is when objects are under no influence at all. There are no forces, nothing pulling on these objects at all, except for gravity itself. Okay. So first of all, consider a hammer and a feather. If you drop them at the same time, which one will land first? Now, most of you have probably answered that the hammer would fall first and hit the ground first. And then the feather would just gently float to the ground. So my question is, why? Why is it that the feather floats gently to the ground, whereas the hammer goes quickly? Hopefully your answer was something about air resistance. The air flowing through the feather causes the feather to slow down. It causes the hammer to slow down as well. It's just that the hammer is heavy enough that it cuts through the air pretty easily. But the feather, however, since it's lighter, is more subject to air resistance. But what if we get rid of air resistance completely? Now which one will land first? Well, Galileo Galilei solved this question in the 1600s. His answer was that all objects will fall at exactly the same rate. In other words, a hammer and a feather fall at exactly the same rate. There is a video in the supplemental materials page on Falcon Online that actually demonstrates this, where they took a big chamber and turned it into a big vacuum, took out all the air, and actually dropped a bowling ball and feathers at the same time, and sure enough, they landed at exactly the same time. Now again, this ignores the effects of air resistance. So if you just go outside and drop things off of your roof, you're going to see the feathers slow down. But if you can get rid of the air, they would fall at exactly the same rate. All objects are accelerating downward due to gravity. The acceleration due to gravity has a value of 9.8 meters per second squared. That is the value for all objects. Every object at the surface of the Earth has a downward gravitational acceleration of 9.8 meters per second squared. Now this comes up all the time, and so we often shorthand it by assigning it this lowercase g variable. So g equals 9.8 meters per second squared. However, do always remember that this acceleration is downward. Since acceleration is a vector, that means that we have a downward or negative acceleration. So that negative is going to have to come up in our equation in just a bit, and I will show you how to do that in the next slide. So let's take a situation where you drop a rock. You're just holding the rock, and we're going to define our starting height as 0. And we're going to see how much the ball falls after every 1/10 of a second. And so since it's falling, that means each height is going to be negative. Okay. Now you see all the values here, but we're going to actually start calculating them. Okay. So to calculate the position, we're going to use this kinematic equation that the position is going to equal your initial position plus initial velocity times time plus 1/2 of the acceleration times the time squared. Okay, well, we can simplify this a little bit. What's our initial position? Well, we defined our initial position to be 0. So that value is going to be 0. What's our initial velocity? Well, we're holding it, and then we drop it. At the very split second where we drop the rock, it's not moving. So our initial velocity will also be 0. And what is our acceleration? Our acceleration is g, 9.8 meters per second squared, because of gravity, but it has to be negative. And so our equation starts looking like this. Y is equal to, these two terms are 0, minus 1/2 gt squared. This is the equation we'll use to calculate our position. What about velocity? Well, we have this kinematic equation. V is equal to v naught plus acceleration times time. Well, like we already decided, our initial velocity is 0, and our acceleration is g, but downward, so that means that velocity is equal to negative gt. Okay, so we're going to use these two equations. And we're going to plug in every tenth of a second, 0.1 seconds, 0.2 seconds, 0.3 seconds, so on, to calculate both your position y and your velocity v. So if we plug it into our position y, then we get negative 1/2 times 9.8 times 0.1 seconds squared, which when you plug that all into your calculator, you get negative 0.049 meters, or it's fallen 4.9 centimeters. How fast is it going? Well, it's negative gt, so negative 9.8 meters per second squared times 0.1 seconds. And so that gives us a velocity of negative 0.98 meters per second. Okay, do it again for 0.2 seconds. So position, it's same equation, but now our time is 0.2, so it's negative 1/2 times 9.8 meters per second squared times 0.2 seconds squared. Plug that all into your calculator, you get negative 0.196 meters. And your velocity is negative 9.8 times 0.2 seconds, which will be a negative 1.96 meters squared. Excuse me, not meters squared, meters per second. And finally, after 0.3 seconds, we do the same thing. We get a position of negative 0.441 meters and a velocity of negative 2.94 meters per second. Now, you can keep going and do this for every tenth of a second, and you're going to find that you get all of these values. These are the values we just calculated, and then at 0.4 seconds, 0.5 seconds, and beyond, this is what you would get. And then these are the graphs showing the position. This is a common position graph when you have a constant acceleration. Then you have a velocity graph where you have a steady slope, constant slope. So this is your velocity versus time under a constant acceleration. Then here's your acceleration graph. You have a constant acceleration of 9.8 meters per second squared.